I want to explain what we're trying to do. So what we're trying to do, we're trying to solve theory of elasticity problems in an easy way. Do you agree that it's very hard to solve 15 equations and 15 unknowns at once? Well, Airy came up with a way that you can do it for certain problems, 2D problems for the most part. And he came up with this biharmonic equation that if you solve, no, you satisfy the strain deflection relationships, and you also satisfy the compatibility equations, and you also satisfy the equilibrium equations at once. So you don't have this mine of equations that you have to solve, but you got it down to one equation. Does that make more sense now? That's a great question. Sorry if I did not explain it well earlier. But why we don't walk through some examples now? So I'm going to cover some examples on Airy stress functions, some examples so you can see them. The first example, and I'm going to start simple and then I'll complicate as we go. Okay. By no means I'm asking you, I'm not going to ask you by any means to come up with these Airy functions because somebody sat down for maybe months to figure it out. But you should at least understand how these are used to solve various problems. So the first one is a classical problem of a tension. So you have a bar or beam under tension alone. This beam has a height of 2c, as you can see there. And I'm going to use a pointer here so you can kind of see better. And it has a width of 2L. And on each edge, a load applied is provided there at x equals L and at x equals minus L. The top surface is free. And anytime you're dealing with Airy stress functions, you're gonna see that the boundary conditions for the surfaces that have no stresses also need to be applied. So everybody here should be clear that this edge and this edge have forces applied, and this edge and this edge is free of any forces. As a consequence, however, those boundary conditions need to be satisfied for whatever Airy stress function I select. Here, the person chose an Airy stress function that looks like this. It says that phi is a times y squared. Understand it so far? Yes? But sigma xx, and I'll let you do it at home, but sigma xx is related to the Airy stress function. It's related to the Airy stress function through this derivative here. Let me remind you. Here at the top, you see sigma xx equals a second partial phi respect to y squared. Do you see that? Top left. So I'm going to go ahead, show you that get it for one of them. So sigma xx equals second partial phi respect to y, right? You can see quickly that if I plug that in, I'll get twice a sub naught 2. I'll let you do it. First partial respect to this one is 2ay. Second is a2a. That's what I get. I'll let you try it at home also, but you get the sigma yy and tau xy is 0. And you may ask me, oh, does that make sense? Looking at the problem? I think it makes sense. Let's check it out. I'm taking a beam and I'm stretching it. Do you expect any stress to show up this way? I think it makes sense that it gives a 0. Also makes sense that there's no shear stress. I don't think that this is going to start distorting this way when I load it up. If it's a composite, maybe, but this is not a composite problem. So I think this makes total sense. And I also note that the stress is, and this is very interesting, do you know that the stress of this boundary and this boundary, using Cauchy's relationship, tells you, if I look at the tractions, look at the tractions there. Tractions is what? I have what? I have 1, 0, the traction, say at this surface here. And that has to be equal to sigma xx, right? Sigma xy, sigma xy, sigma yy, times the normal. Times the normal. And the normal to that surface is 1, 0. All this you try it at home, but what you get is this traction T, sorry, the traction is T and 0. That's the traction, right? At this surface. You find that when I do this multiplication, sigma xx equals T at that surface, at this surface. So that's your boundary condition there. You can also check later at home that at that boundary, sigma yy will be 0, and then tau xy will be 0 at that boundary. You can check it at home when you do this multiplication. We're not going to do it here, but I think you will find that when you do it at home. So now I'm going to move to a strain deflection relationship. Strain stress relationship. I already said that sigma yy is 0 from the previous equation. So I end up with epsilon xx equals T over E. Very easy so far. I also find that sigma y is 0. So the strain is minus nu times tension load applied divided by E. And that makes total sense. If you recall, I told you that when you take a bar and you stretch it, what do you think happens in the other direction? The strain, what happens? Yeah. So thank you. So it contracts, right? And it contracts because of the Poisson ratio effect. And it's showing up. You can see it's showing up there. So it makes total sense. But I can take now, so notice how I found stresses, right? I have stresses now. I know strains because I have this is equal to that. And now I can integrate this equation once, each of them. Very easy. I didn't do it here, but you can integrate it once and you get deflection. And you integrate it here and you get deflection for V. You get both. Okay. Any question on that first example? In this next example, example 2, we're going to study a beaming bending. So I have this beam under bending load. And you've seen this before in mechanics and materials. And you know that the loads, the boundary conditions are very simple. You can see that, for example, you can see that stresses on each of these surfaces. Sorry, I apologize. Let's go through the boundary conditions one by one. So the beam is 2L in length, 2C in thickness. And there's a bending moment applied. Okay. Let's look at the first one here. So it says that at y plus minus c, so that's here. That's at the top and the bottom surface. That top and bottom surface. Do you agree that top and bottom surface has no tractions applied? You don't have anything applied there. So therefore, these two, this one and this one should be 0. You can also see that at x equals plus minus L, there's no shear applied. Do you see any shear applied? So then one also should be 0, right? Using Cauchy's relationship. I'll let you try it at home. If you take this surface and find the normal of that, say, like, look at this surface here. If I take that surface, in fact, let's just do it so you can see visually what I mean. I want to make sure this is clear to you because that's where the concept of Cauchy's relationship makes sense. So let's look at this surface here. That surface there. What normal is that surface? That normal is 0, 1, right? Because it's pointed upwards. So 0, 1, that's the normal. So that's n hat, right? The stress is what? Stress, you guys already know what the stress is. Sigma xx, sigma xy, sigma xy, sigma yy. And remember the stress tensor is symmetric because of the moment equilibrium equations. This should be equal to the traction. Do you agree there's no traction applied on the top surface? 0, 0. I think you'll agree with me that when you multiply this out, you multiply this row times this column, you get sigma xy equals 0. That's what that is. If I take the second row and I multiply that by the vector, I get sigma yy times 1 is 0. That's what that is. Okay, is that clear? I will not do this edge because I think that's quite easy also. Okay, so I just did one of them so you can see how it works. Now let's examine this here. This is saying the integral of sigma x at this boundary and this boundary dy is 0. If you think about it, that's a force resultant. And you can see there's no force applied here axially, right? You do see there's a moment applied, m, and that's related through this equation, sigma x times y dy. Why is that moment? Let's think about why that's considered a moment. And I'll draw the cross-section for you, and I'll cover that in a later lecture when I cover beam theory. But I want to make sure that the concept is clear to you when I do it. I want to explain why that's the case, why that equals the moment. So let me draw, if you don't mind, I'm going to draw this cross-section here. And I'm going to zoom in, and I'm going to make it in 3D. Okay, not to confuse you, but that's kind of 3D. I apologize if it's not beautiful. We'll take x going that way, and I'll take y going that way. Let's look at that carefully. So what I have here is, let's say I have an element sigma xx. That sigma xx with this moment arm, there's a moment arm y. Is a moment dm equal to sigma xy times y? That's force times distance. So what I've done then is to integrate this to get that. Now you see a minus sign. That minus sense makes perfect sense. I invite you to go to Starbucks so people think you're crazy and start making signs with your hands about, which way it's going. I don't know if that happened to you, but when I was studying back in school, I remember people look at me, what are you doing with your hands? Oh, I'm just studying if it's clockwise, I'm counterclockwise. And they're like, for real? Yeah, that's what I'm doing. But you can kind of do that, I'll invite you to be crazy, do that in the bus or something. But it's kind of fun. Try it at home. You'll see that this negative sign will come up. If it's not clear to you why that sign comes up, please come to me or Miramai and we'll explain it to you. But I want you to try it at home because only when you try it at home, it makes sense. I don't know. Every time I do this sign convention thing, I feel like I need privacy. I need to kind of do it on my own, like kind of, play it around with it. All right, so that's how I feel. The stress function here that was selected by someone, again, I'm not asking you to be an expert on how to come up with this, but you need to understand how they're used. So phi was selected to be that. It turns out that that's a very good one. It actually does a great job of trying to figure out, it actually does a great job of it actually tells you how things work very well. Okay, so when you take the derivatives associated with that, you get that sigma xx will be equal to this. And then the shear stresses and sigma yy are 0. They don't show up. So that bending only problem works very well. Again, I invite you to do it at home. I'm pretty sure I have a mistake because sigma xx, right? Second partial phi respect to y should have given me, so I have the first partial of this is 3ay squared. If I take a second partial, I should get 6ay. So there's a y missing here, and I apologize for that. Okay, do you catch my mistake?
Looks like there might be a y on there after the O3.
Yeah, you're right. There's a y, but it showed up in the subscript. I apologize for that. So let me fix that here. I'll circular it. That's supposed to be normal y. I think you can do it at home and check it out. You guys are very capable. You can also prove that for pure bending moment, you get the sigma xx equals this. by applying this integral for a square beam. If you did it for a square beam, where you have a square cross section, you'll get that that's equal to that as well. I'll let you do that at home as well. All you have to do is plug this in here, the 6ay, plug it in here. You get 6ay squared, integrate that, and then you'll get the equation here at the bottom right. So you can use Hooke's law. Again, you can use Hooke's law, right? Once I know stresses, can I get strains? How can I get strains if I know stresses? The constitutive law. And once I know strain, do I know deflections? And once I know deflections, I'm golden. I know if my design works. Okay. So one of the things you need to do when an Airy stress function is provided to you, my advice is to make sure that it satisfies the biharmonic equation. That's one of the things you should check. You can also see that it satisfies very, very easily the equilibrium equations, and it usually does. So it's a pure bending problem. What would I move? A different way of doing the formulation, that just as a summary, right? So I gave you two examples: tension, bending, and thank you for transcribing my notes. I gave her my notes from school, and she transcribed them. So this is her work. So thank you for doing that, Muramai. Thank you. I want to describe it how it's explained to me in school. The way I explained so far is from my own book, but also other resources. This is more of a summary one more time. So it kind of keeps going to your head little by little, right? You know, when it comes to studying, it comes down to when you plant a seed, right? You have to give it water. And you cannot give it too much water because it gets flooded. Do you agree with that? But you cannot give it too little because it will never grow, right? So you need to be consistent. So I view this learning experience as if it was micro drip irrigation. It's going to your head slowly, little by little, and you have to keep repeating it to yourself. Personally, and I'll be just very blatant with you, right? I haven't looked at this material, although I have my own book and I've written it before. When I looked at it, I'm like, I don't remember this. That's okay. That's okay. But I understand it because somewhere in my brain, I learned it once, right? So I really encourage you to take the time, sit down, and let it stew. I like to call it let it stew. You know, one approach that may work, you fall asleep and the book is open the correct page with the Airy stress function and it's in your head, near your head, and maybe by osmosis, it will get there. That's one approach. And what I mean with that, let me explain what I mean with that, right? So a lot of these lectures takes me a while to prepare, right? What I mean with that is the subject becomes your best friend, really is what I'm talking about. So you're studying it, and it's also maybe before sleep is not the best thing for your eyes. I agree, but you're kind of near it. You're thinking about it, right? So let us do there. Let me cover this a different way of doing it. So the body forces as explained here can be written as a function of something else. I'm using different variables on purpose. X1 used to be X, X2 is Y. I used V earlier, I'm using omega. We're changing everything. So you know that it doesn't matter what you use, it's a constant that matters. Body forces depend on these variables. And you can show that by plugging these into the equilibrium equations, you get these equations. I already told you that Airy came up with this function phi that your stresses become this. I already covered that with different variables. I use sigma xx. Here I'm using sigma 1,1. Earlier I had used sigma yy. I'm using sigma 2,2. Earlier I had used sigma 1,2, but this is sigma xy. That's okay. That's a different convention on how things are explained. But the concept is very simple. What you're trying to do is to solve these things in an easy way. And Airy provides you that path to getting it done faster and easier. I also showed you how the plane stress and plane strain relationships turn out to be this biharmonic equation with this weird symbol, which is right here at the bottom. I'm expanding it for you so you know what that means. This here is this right there. And here at the top, the omega, if you have body forces, that's the way it looks. If there's no body forces, these ones go to 0, and you get the 1 here at the bottom. So that's the equation that you need to solve. And if you solve this equation, you solve the compatibility equations automatically. You solve the equilibrium equations automatically. All you have to do, like you've seen in the 2 examples I gave you so far, all you have to do is to impose the boundary condition and make sure the boundary conditions work out for the problem of interest. Everything clear so far? I'll pause there. Okay. So moving on here then to the example number. Now these are the real examples. The bending and tension, those were more for you to kind of see how it works in general. These are real examples, right? So in this problem, this is an interesting problem. I like it very much. What it shows here, it shows a plate. And that plate has a tension load applied in this surface here at the top. Also, there is a tensional load applied here on the right surface. Do you see that? This tension load applied C. The magnitude is A and C. That's what that is. And then you also have this shear load applied, which is B. Can you guys see that so far? So those are the amplitudes or the values of those forces, traction forces. Airy stress function for this problem was given as A over 2 x1 squared plus B times x1 x2 plus C half x2 squared. That what was provided there. It turns out you're automatically satisfy the biharmonic equation. I invite you to do it at home so you can see that is the case. It will give you equal to 0. We'll probably ask you in a problem to show that. We may ask you, hey, can you show me that satisfies the biharmonic equation? You can then find sigma 1, 1 through this equation, sigma 2, 2 through this equation, and sigma 1, 2 through this equation because you know these things. Now, I think everybody agrees with me that can use Cauchy's relationship to look at what's going on at this surface. And you will see that the vector, the normal to this surface is 1, 0, the normal to that vector. And you know that the traction applied to that surface is C0. The vector is C0 because C is the Tx and 0 is Ty. There's, whoa, is there a Ty? There is a Ty, it's B. There's a Ty. So I want to make sure we got that right. So there is a traction in that direction. So it's clear to you because I kind of jumped the gun there for a second. Excited about nothing being there, but there's something there. Why we don't do it quickly here so you can see it with me. So the traction is C minus B according to the problem statement. Usually this would be positive B, but the problem statement is using an amplitude as minus. So it's fine. It's for the purpose of this problem. Times sigma xx, sigma xy, sigma xy, and sigma yy times the normal to that surface, which is 1 and 0. That normal here. That's the one I'm looking at. When you do that, you'll get that. You'll get I'm sure you'll get the thing at the top. Just do it. Okay. Example number 2. And this actually is a solution to the problem when you actually work it out. You may ask me, oh, I'm not seeing it. I see some of your eyes looking at me weird. Let me show you. Let me show you, all right? Let me show you that your class in pre-calculus worked out. What is the second partial of phi with respect to x2? That's this goes away. The first partial will give you bx1 only. No. Yes. Yes. And then this one you get cx2. No? So what is that giving you then? C for second partial. Then do this one. you'll get A. Do this one, you'll get minus B. Guaranteed. Just do it at home. Let's not do it here. Try it out. It's just basic differentiation. Example 2, somebody came up with this clever example. In this example, that was given to me back then, and I haven't seen these ones in any book, so that's why I wanted to show them to you. They're kind of cool. In this problem, this is a Airy stress function that's provided for actually a very complicated problem. It's actually in equilibrium too. So you have shear forces applied on the top surface that cause bending. You have shear forces in the bottom that cause bending. So a lot of these problems, the person, not me, had this problem given to them. And they said, okay, what is a stress field here for this problem? I'm interested in this. So somebody came up with a phi that makes this problem work. Is that what you're saying? Well, sure. But in reality, this is true. This phi corresponds to this problem. Can we say that? And this problem corresponds to this phi, vice versa. So yeah, so this problem is given to you traction like that, and then with bending forces applied here. This is a more complicated problem, but you can see here that the phi is provided like this. It actually turns out that for the barharmonic equation to be satisfied, the only way that can happen is if A plus 2C plus E is 0. So that's one condition. And then you can then look at other conditions too. You can calculate sigma 1, 1, sigma 2, 2, sigma 1, 2. You can impose the boundary conditions as well. And it turns out that for this particular problem, when it was developed, the top and bottom surface see a shear stress of D half times H squared. H is 2H is the height of this. But there's another problem where somebody came up with a phi, it gives you these stress fields, and you can then solve for A, B, and C. So it's and D's, well, D's provided to you. So it satisfies the boundary conditions. That's just another example. So I'm just giving you like some cases so you know what they look like. Please. If you have to solve for A plus 2C plus E, if you have to solve for A, B, and C and all that, the answer, if the answer is in reality, yes, because I want to know if I have this material, I want to know where it fails. And you can see that phi depends on A, B, C, D, E, and I need to solve for those for me to be able to determine where it fails. And all I'm trying to point out to you guys is that A, B, and C, and D, and E can be found through, first, you have the biharmonic equation that forces this to be 0, but then you also have the boundary conditions. And the boundary conditions have to be satisfied. In this problem, for example, sigma 2, 2 is 0 for the boundary. And then you also have to make these ones pan out too. But you also know that sigma 1, 1 and sigma 2, 2 and sigma 1, 2 is those things. And then you can basically solve for A, B, C, D, and E. You have enough equations and enough unknowns. Now, here, in these examples I'm giving you right now, I'm not doing it for you. I'm kind of sketching it out for you so you can see there's Airy stress function for each of these cases. But I'll walk you through one example so you can see how to solve for those. I'm just kind of giving you some examples on Airy stress functions that came up for particular problems. I solved it already for 2 cases, the bending and the tension. These 2 cases, I'm just showing you the sketch on how that will look like. Because solving it to me is less interesting. That's a mathematical problem. But understanding physically what is going on is more important to me. Is that clear to you? Yeah. So let me give you another example so it's even more clear, right? So look at this surface at the top. That surface at the top, you agree that's shear? So you can see there that the shear better be D half H squared. Why? Because sigma 1, 2 is D half X2 squared, and X2 takes a value of H at the very top. So in the problem statement, when this was developed, somebody thought of that. Somebody said, I want to apply a shear stress of this much. So D is known in this case. Sorry, the only thing that's not known is A, B, C, and E. So you have three boundary conditions. You have this biharmonic equation that gives you four unknowns and four equations. So it's possible to solve. Here's yet another example, but in this example is a special case where they took the top tractions and eliminated them. And you can see here, they eliminated it by subtracting this much. It works out somehow. You can see here the sigma 1, 2, evaluated at plus minus h is 0, like at the top and bottom, there's no traction force anymore. It works out really nice. This equation satisfies the biharmonic equation, but you have to find the variables, like you will get an equation like this, but you will get it for this. Now let's walk you through this problem. Okay, this is the first one that you're gonna see. I'm gonna walk you step by step. Does that make sense? Like the ones that I was showing before, examples 1 through 3, where here's the Airy stress function that works very well for this problem, and this is a sketch of what it looks like. I'm gonna choose one particular example and go deeper so you can see all the steps. Is that fair? Okay, I like it when that gives me confidence that I'm doing it well. Any other questions you have before continuing about the sketch? For a particular problem, somebody already did a lot of homework for you. They came up with the Airy stress function for a particular problem. Second step, make sure that it satisfies the biharmonic equation. If it doesn't, you have to figure out what constants make it work. If you don't have enough equations to make it work, you need more equations. Where those equations come from? The boundary conditions. You apply the boundary conditions, and by applying the boundary conditions, you can then solve for the coefficients that are missing. That's how it works every single time. Once I know the phi, the Airy stress function, I know the stresses. How do I know the stresses? I know them because I have these equations. Sigma 1, 1 is the second partial phi respect to x2 squared and so forth. That's how I know stresses. Once I know stresses, do I know strains? Yeah, through the constitutive law. Once I know strains, do I know deflections? Yes, I know, through a strain deflection relationship. That's how it works every time. In this problem, however, phi is given to you, and it's given to you for a cantilever problem where the load P is applied. It turns out that if you plug this into the biharmonic equation, it works out really beautiful. It gives you 0. You can then calculate sigma 1, 1, sigma 2, 2, and sigma 1, 2 by plugging this phi, plug this phi into these equations here. Let's do one of them. Sigma 2, 2 is a second partial phi respect to x1. You can see here very clearly that there's no x1 squared. So therefore, that has to be 0 for sure. So these ones are easy. Remember that we discussed that, but we also discussed applying the boundary conditions next. That's what I did here at the bottom. Stress-related boundary conditions. At x2 plus minus h, top and bottom, sigma 2, 2 is 0, and sigma 1, 2 is 0, top and bottom. So what do? You plug in here what x2 is at the top, and you plug in here what x2 is at the bottom. x2 at the top is how much? Is h, or minus h. That has to be 0 at those two boundaries. Is that clear what I'm saying? No tractions here, no tractions there, right? The location of this surface and this surface is at x2 equals plus minus h. I can plug that into this equation and make sure that that is 0. That when I plug in h there, I get 0. Does that make sense? I also know that at this boundary here, the one at the very left, at the tip, I know that there's no axial stress applied. So that has to be 0. The integral of that, there's no resultant force going axially. So that's 0. But we know that the shear stress integrated through the thickness is minus P. At the very least, we do have that one. This one right here exists. And then there's no moment. There's no sigma 1 times x that causes a bending moment at this surface here. These are the only boundary conditions that we have on this surface. We'll have similar boundary conditions on this end, although suspect that typically if you have a cantilever beam, that this end will be fully fixed. It will be fixed. Like meaning is the deflections are 0 at this edge. But right now, all we're trying to do is provide the stress boundary conditions, the traction boundary conditions. Those are the ones we're tackling now. I'll pause there for a minute. Wait to see if there's any questions. So yeah, so one more time, the sketch, given the Airy stress function, the biharmonic equation, you have to check if it's satisfied. In this case, it's 0, exactly 0. Then you get the individual stress components using these formulas provided here. Next step, applies the boundary conditions. The boundary conditions are very simple. At the top surface, I usually like to start with the ones that are 0 tractions. Top surface has nothing in the 2 direction or tractions, top and bottom. The remaining surface is the one here on the edge, the one here at x1 equals minus or L or 0, I guess, this surface here. The one here, there's no resultant force applied. That's axial. There's nothing going left. There's also a traction load applied downwards. So that's where that's coming from. And then finally, there's no moment applied. So that's 0. And so what I'm going to do next is go ahead and now try to apply some of these boundary conditions. So you can see here, let me take that question then. So sigma 1, 2 is not 0. Sigma 1, 2 is 0 at the boundary top and bottom surface. Sigma 2 is actually this equation here on the right, minus a minus b half x2 squared. So it can vary across the whole beam, right? So now looking next to the next step here, let's apply the boundary conditions. I did it here for you. Sigma 2, 2 is exactly 0. You can see there it's satisfied exactly. Sigma 1, 2, a plus minus h gives exactly what I discussed with you. Minus a minus b half h squared equals 0. You can solve for a, you get minus bh squared. And then sigma 1, 2 turns out to be b half h squared minus x2 squared, which means that the shear stress, and you learned this back in school in mechanics and materials, that when you apply a load to a beam, you develop a shear stress that's parabolic in nature. So you can see it showing up here that you get the max stress at the tip, the mid plane or neutral axis, and it's 0 at the top surface and bottom surface. You can see that's working out exactly how you learned it back in mechanics and materials. You can also integrate, you have this equation here now that you can use. Sigma 1, 2 is this equation here. Plug that into this equation, and that gives you that B is this much. Now you know B, you know A because A is related to B through this equation. Therefore, I know everything. I know A and B. I'm ready to find phi. If I know phi, I know sigma 1, 1. I know sigma 2, 2. I know sigma 1, 2. I know strains. I know strains across this whole beam. Now I can plot it in MATLAB. You have a question? And because I know that, I can get strains through the constitutive law. Right? You can see it there. So I have that. The strains. Now I can integrate epsilon 1, 1 respect to x1 and x2, epsilon 2, 2 respect to x1 and x2, integrate each of this to get the strains, the deflections on how they vary across the whole thing. Yeah, I did it here for one of the cases. So I integrate respect to, say, x1, because that's the derivative respect to x1. This is what I got for epsilon 1, 1. Integrate that respect to x1, and you get px1 squared x2, 2 divided by twice e1, ei. E is the modulus, I is the modulus, the second moment of inertia. And then because you're integrating respect to x1, you get a constant. Correct? I can then integrate this respect to x1. When I do that, there's actually an error. Because epsilon 2 is partial u2 respect to x2, not x1. So that's an error. But the integral looks okay. So I integrated that. That looks okay. And then I have epsilon 1, 2, which when I integrate it, I get this equation here. Now, how do I solve for those functions f1 and f2? This function f1 and f2 need to be found. To solve for those, what you will do is impose this boundary condition that's fixed. You know that u and v is 0 at x1 equals L. When you plug that in, you can find those functions. You have two unknowns, two equations. For a beam that's clamped with a load applied P. Do you guys see that? Let me sketch it up for you one more time. Let me sketch it for you one more time. Number one, the Airy stretch function will be provided to you for particular problems. You check that the biharmonic equation is satisfied, because if it does, it satisfies the equilibrium equation exactly and the compatibility equations exactly. But if it doesn't, then you have to figure out what constants need to be added so it gets to 0. So that's your first equation. You know, sigma 1, is related to phi through the three equations I provided you. Sigma 1, sigma 1, 2, sigma 2, 2. And if you want to use x and y, that's fine too. Sigma xx, sigma xy, and sigma yy. Impose the boundary conditions. You know what the boundary conditions are at each of the surfaces because they're provided to you. Make sure those are enforced and solve for as many constants as you can. And usually you can solve for all the constants very easily, as I showed you just now. Finally, you can get the strains by connecting it through the constitutive law, because they're connected to the stresses through the constitutive law. And then once you get the strains, you can solve for deflections by integrating the strain deflection relationships, but that'll give you more constants now that I have to solve for. Those are found through looking at the boundary conditions of the problem. In this case, the beam is fixed in one end. Use those to solve for the unknowns of the problem. Is the sketch clear to you? Example 5 is actually very interesting. This is kind of like reversing the problem for you. It tells you what the stress is. I'm telling you what the stress is. I want you to tell me what the Airy stress function looks like. I don't particularly going to give you a problem like that, but I think it's worth seeing how everything's interconnected. And I'm okay with that. That's why I'll go through this example. Given this stress distribution, verify that these stress states represent a solution to a thin plate. 2, obtain the stress function, the Airy stress function. And 3, tell me what the shear and normal forces are along the boundaries of y equals b, which is here, and y equals 0 here. Sorry, 0 is there, b is there. So 3 problems, 1, 2, and 3. Let me walk you through each of them. All I'm trying to show you is how you approach it, okay? So for number 1, you know that this is how the sigma xx is related to this. I gave you that. So that's given to you, right? That's given to you. So that's related to that through here. I can check out, you can check it at home that the biharmonic equation is satisfied, has to be satisfied through this equation. That has to be the case. You can check also that this one, that phi, is equal to, this sigma yy is equal to that. You can check that at home too. You can also check what tau xy gives you. Tau xy is this. I gave you this already. So this is given to you. You can check that you actually get this when you do it. And you can check that the biharmonic equation is fully satisfied. And if you're wondering where these equations come from, I want to remind you where it comes from. You may have forgotten, but they're coming from here. That's the equation we're using earlier, right? I combined the two equilibrium equations into that equation, right? You guys remember that? So you can just, if you satisfy that, you kind of satisfy the biharmonic equation. Yeah, so you guys can check that. This one works. It gives you 0. That's good. The second part of the question, so this is a good solution then. That's what he's saying, that the stress solution satisfies equilibrium, and that's a good thing. It works out. We'll now solve for, now they're asking us for the stress function. Find the stress function. That's part 2. So sigma xx is this much. Integrate it, integrate this once. Then I get this with the extra function there. Integrate it again. And now you get phi with 2 constants now. Any questions so far? What I'm going to do now, I'm going to plug in that phi back into the biharmonic equation. When you do that, you'll get something times y plus this. But that needs to be equal to 0. So it turns out that because this has to be true for any value of y, that each of these coefficients has to be equal to 0. I'm very unlikely going to give you this problem, very unlikely, but I'm just trying to give you a different flavor of the problems that you can get. So that means that this needs to be 0, and that needs to be 0. So therefore, I have these equations here. Now, I can integrate the first equation 4 times. So I get all these, and then I can integrate these 4 times, and I get all this. Constants. Now you can use the boundary conditions of the problem to solve for the constants, for the unknown constants. And there's many boundary conditions. Let's think about that. I actually did it, but let's look at the problem statement. So, well, let me just show you this. How many surfaces we have here for a beam? 2 boundary conditions here, 2 here, 2 here, 2 here. That's 8 already, right? So you will have enough constants to solve for the unknowns. You will have them. Okay. So that was just to give you a flavor. There's another example 6 that comes from a different book. This one talks about a beam carrying a uniformly transverse loading. Interesting problem. You probably studied this back in school. So if the loading is W, then the total load applied downwards is W times 2L. That has to be balanced by this, each of these supports, boundary supports. It's asking to solve for the problem. So let's look at the boundary conditions. So there's no shear stresses applied here at the top or bottom, right? No shear stresses at the top or bottom. You can see that there. At y equals plus minus c. No boundary conditions there or there. At the bottom surface, where y is equal to c, which is here the bottom surface, there's no traction load applied, so that's 0. At the top surface, however, there is a traction load applied. And you can see it there. That one right there, W. That's where that's showing up. Let's look at the other boundaries that we have. The other boundaries I have are this one and this one. At this boundary and this boundary, there's no force going that way. So that's 0. There's no moment applied. Do you see any moment applied? That's 0. However, the shear stresses are not 0. There's a value to them. And that's this one and this one. That's a shear stress. So that has to be the case for those two edges, right? Tau xy exists in this surface and this surface. I have 6 boundary conditions. This is a trial function to give you, or somebody thought about the problem in a lot of detail. But this trial function has to satisfy all the boundary conditions. First, I have to find what the stresses are. I have to figure what these are. So this is what's given to you, right? For a given problem. You have to find what these are. And when you do the calculations, I will give an example. Right? When you do that, you'll get the thing there. And so forth. You can get the other ones. Now you know the stress. Again, step number 1, biharmonic equation given to you. Step number 2, get the stresses in terms of the coefficients that are unknown. Step number 3, apply the boundary conditions to the problem. I started with the boundary conditions because I like to understand the problem before I start solving it. And so I like to spend time on that. But you can do whatever order you want. The most important part of the whole problem is the boundary conditions. If your boundary conditions are wrong, everything else is wrong. Because everything else is mechanics, math. I did it here. I used the first 3 boundary conditions to solve for these constants. This one, and this one. When you apply these 3 boundary conditions, you're able to find these 3 constants. And when you apply these boundary conditions, you're able to find the remaining constants. And the remaining one here is this one and this one. And do this at home, step by step. Remind, if they do it correctly, they get 20 points extra credit. I know it's more work for you or the grader, but that's what I'm providing. I'll continue here. Stresses in the beam are therefore found in this manner. These are the stresses found in this problem statement. I found all the constants. When I write it out, this is what I get. Is that clear? If I know stresses, do I know strains? If I know stresses, do I know strains? If I know strains, do I know deflections? And that's what happened there. I know stresses, I know strains. I know strains, I know deflections. So I basically related that and then found the deflections of the problem. And this is a textbook problem that has been covered before. I also want to give you 50 points for your engagement today and in the previous lectures. Thank you for your engagement. Any other questions you guys have?